Hello, physics students. I wanted to do a quick recording and just go through and talk about the simple harmonic motion equations. So, the two main equations in this module are the equation that relates the period of a mass on a spring to the square root of mass divided by a spring constant, and then that's multiplied by 2 pi as well. And what this implies is that if you increase the mass on the spring, then the period increases. It takes longer to complete an oscillation. And it also implies that if you increase the spring constant, that the period of oscillation goes down, or in other words, it vibrates back and forth faster with the increased spring constant. It also, a kind of stranger application of this is that if you do a little bit of algebra and solve this equation for k, that you'll see that if you graph the period versus, or actually period squared versus the mass, that that can also be related to the spring constant. With the pendulum, the equation is period equals 2 pi times square root of L over G. So that implies that the longer the pendulum is, the longer the period becomes. And also, if you were able to go to an area where the gravitational field was different, that the larger that gravitational field becomes in the location where the pendulum is held, then the shorter the period of the pendulum would be. One application of this is with, say, a grandfather clock. The gravitational field of the Earth can change from one location to another. Generally, with altitude, the gravitational field decreases. So there's a small adjustment screw that allows you to lengthen or shorten the pendulum in the grandfather clock to make it keep time dependent on the location that it's or the location where it's placed. Now, there's also this relationship between period and frequency, and this shows you the period is inversely related to the frequency, and also this gives you a way to solve for angular frequency if you need that instead, even though we haven't quite gotten to that. That'll probably be more important to us in rotational motion. One more equation that you have encountered in this unit is the one that relates the position of an oscillating object to the amplitude times the cosine of 2 pi times the frequency times the time at which the observation is taking place. Now, keep in mind that since it has frequency here, you could replace frequency with 1 over t. So then this equation would be 2 pi times little t, which is again the time at which this observation of position is occurring. And then that would be divided by the big T, which is the period. So this equation has two different forms, and one has the F in it. The other one has this term inside of the parentheses divided by period. When you put this into your calculator, this is a measurement in radians, and I suppose that would make sense if you think about it in terms of T, or big T period, because the little t divided by the big T would be a ratio of the time given to the time to complete one complete oscillation, and then multiplying by 2 pi puts that in radians. And that's important because when you use this equation, it's necessary for your calculator to be in radian mode, otherwise you won't get a correct answer using this equation. So I hope you find those few things helpful, and best of luck as you complete your test on this unit.